This video is about a new approach to training language models. Specifically, it allows you to move the probabilities of a language model away from bad answers and towards good answers. Direct Preference Optimization, or DPO for short, is a type of reinforcement learning. It's a more efficient type than has long been used by companies like OpenAI and Meta in developing Llama 2. And with this DPO technique, it makes it much easier to fine-tune models towards a chat format that is aligned in a similar way to those commercial models available. For our agenda, we're going to take a look at how normal training works, standard fine-tuning or supervised fine-tuning, as I've done in previous videos. Then I'll contrast how direct preference optimization works and why it's a bit different in terms of a technique, and it's useful in a different and complementary way to standard fine-tuning. Then I'll show you two DPO datasets. The datasets need to be in a specific format if you're going to use the Hugging Face trainer that we will use today. And then I'll walk step by step through the training notebook I've developed for doing direct preference optimization. By the end of this tutorial, you should be able to take a model you've developed, a language model. Ideally, you do some supervised fine-tuning to get it into a chat format. And this will allow you to do the final stage of aligning the model. Another way to think of that is moving the model probabilities away from bad answers and towards good answers. That will make sense as we get a bit deeper into this video. Let's start off with a description, very high level, of how standard training works. Standard language model training involves penalizing the model based on what it predicts for the next token versus the actual next token. For example, if you feed in a phrase or part of a phrase that says the capital of Ireland is, and you ask the model to predict the next token. If the model predicts Dublin, then you wouldn't penalize it because that answer is the next token here in this sentence. But if it says something like Cork, then you would penalize the model and back propagate through. So fundamentally, language models are statistical models that look at the frequency of information that is in the training data set. If I train a language model with the capital of Ireland is Dublin, the capital of Ireland is Dublin, the capital of Ireland is Cork, well, it will see Dublin more frequently, and so that is more likely to be returned when the model predicts the next token. If I want to bias the model towards saying Dublin with a very high probability, I can just keep feeding in the capital of Ireland is Dublin, the capital of Ireland is Dublin, and eventually the relative frequency it is seen for Dublin will be much greater than Cork, and so it is going to respond with the word Dublin as the answer. And that, if you generalize it, is how language models work. They're statistical. The more data you feed them a certain format, the more it will bias the model towards that answer. Let's just look at a simple example here, where we have a data set with Dublin as the next token 10 times and Cork as the next token 1 time. If we train on this data set, the language model is very often going to predict Dublin as the next token, because it has seen it so many more times in the data set. Now, if we wanted to increase the probability even higher, we would just have to add more and more and more data that says the capital of Ireland is Dublin, so that we increase the probability of Dublin being the answer. Now, by contrast, let's take a look at direct preference optimization. Here, instead of adding more data to the model and penalizing it based on the next token prediction, we're going to do something a little bit more nuanced. At a high level, we're going to drag the probability distribution away from one answer, like Cork, and towards another answer, Dublin. So, as an example, we have a prompt, the capital of Ireland is, and then we're waiting on the next token. And we're going to set up two responses. We're going to set up a chosen response, which is Dublin, and we're going to set up a rejected response, which is Cork. So remember, in standard training, the only data we have is on the actual token, and we just compare actual to what the model predicts, which could be anything. It could be Roscommon, it could be New York, it could be any value. The only input data we have is the actual next token. But here in direct preference optimization, we have a pair of options. We have a chosen and we have a rejected option. And the way that we penalize the model now is not by comparing the actual to the predicted, but rather we penalize the model so that the probability of Dublin of the model we're training, we want that probability to be high relative to a reference model. The reference model is just a copy of the model when we start this whole DPO step. So imagine starting DPO, we have a model, we duplicate it, so we now have a model and a reference model. And during the training, we're going to penalize the model in such a way to incentivize the probability of the model being trained, increasing for Dublin relative to the probability that the reference model predicts for Dublin. And likewise, we're going to want to incentivize the model in a way such that the probability it predicts for Cork should be reduced relative to the probability of the reference model. So you can see how these pairs are being used, and we're trying to increase the probability of the chosen answer and decrease the probability of the rejected answer. Really high level, what we're doing here is imagine a training data set. So you've come along with the model, you've done some supervised fine tuning, it's been trained on 1 trillion tokens. There are lots and lots of data points here within the data set. And in that data set, of course, because we've trained it on the internet, there are some bad answers, some answers that, people have written things on the internet that aren't correct. And then there are some answers we consider good answers, where maybe there's more of these, but there's not enough more to statistically get the right answer all of the time. So we have this data set body with bad answers and great answers. And how direct preference optimization works is by using pairs of answers, by feeding it some pairs, we bias the model away from bad answers and we bias it towards great, ideally great, but certainly better answers. So again, to contrast this with standard training, if we want to bias the model towards better answers with standard training, the only way we can do that is by feeding more great answers. So with standard training, you have to keep feeding in more of these great answers. The bad answers will still be there in the data set, but over time, these great answers will start to dominate as we train on more and more sets of the capital of Ireland is Dublin. Whereas by contrast in DPO, we're penalizing the model for a bad answer and we're incentivizing it for a good answer. Now I'm giving a very simple example here just with the capital of Ireland. But as it turns out, when we look at these pairs of good and bad answers, there are certain statistical attributes about good and what we consider bad answers. And those statistical attributes are then captured by the model. And that helps us to generally drag the model away from worse portions of its training data set and towards better portions of its training data set. And so when we go back to our graph here showing the frequencies, you can imagine that in a data set of the World Wide Web, you again may have a lot of bad data and you have hopefully even more good data. It might be hard to get rid of some of the bad answers. It might be hard to overcome them rather by just feeding more and more data into the model until the right answers kind of win out. And so direct preference optimization gives us a different approach where rather than just adding in more examples with Dublin, we specifically penalize the examples with Cork. So it's like we can almost remove the Cork example, or at least move the model away from the Cork example and moving towards the good example. I'll move now to talk about different data sets that are available for doing direct preference optimization. There are two ones I'll talk about. One is UltraChat and the other one is Anthropic's Helpful and Harmless. The way to think about UltraChat is a series of conversations that have been had in all sorts of models. There are conversations from Falcon models, from Llama models, from MPT models. And some of these best conversations, which we would consider good data, and which also would also include bad responses, we take those and we form pairs, and then we use that to train our model. So this is a synthetic form of data. It works well if you take very strong models. Largely the data comes from larger models like 40B or 70B Llama. And then we use that to train smaller models. In fact, that's how the Zephyr model, which is a fine-tune of Mistral, works. So the authors of Zephyr, which is a Hugging Face team, they took the Mistral model and then they used an UltraChat dataset, which is generated by more powerful models. And this provides a strong compendium of what we can call great answers versus bad answers. And using that data set, it was possible to fine-tune Mistral using DPO in order to get an improved model called Zephyr. One of the issues with the UltraChat dataset is that because it uses other language models that are not completely permissively licensed, that limits the use of Zephyr to non-commercial use. Furthermore, in ranking which answers were great and which were bad, GPT-4 was used, and the terms of the GPT-4 license don't allow you to use it commercially. And so Zephyr is a great demonstration of how you can synthetically produce strong data with large models. That provides you with a good versus bad data set, as graded by GPT-4 in this case. And then taking that data set, you can train these weaker models and basically point the weaker models away from their bad answers and towards their good answers. I'll put up a link below to a data set you can use if you want to use the UltraChat set. The other data set that's available is Helpful and Harmless from Anthropic. It's 160,000 rows. About 40,000 of those are harmless type and 120,000 are helpful. This data set's been around for a while and it's been used to train Llama 2. It's probably been used to train a lot of models. And it does something a little different than just pointing the model from bad answers to good answers. It's also trying to achieve a level of safety and avoid the model spitting out perhaps harmful, dangerous type results. Just as an example, one instruction set that you might see, a type of instruction set you might see in the harmless part of the data set is as follows. The prompt might be, how do I do something dangerous? And the chosen answer, which is what we want to incentivize the model towards, is, I don't know, that's an interesting question. So it's kind of harmless. Certainly not helpful, but it's kind of harmless. And the idea is to pull the model away from giving out dangerous answers. And then the rejected answer might be something like, go and blow up XYZ. And this clearly is some kind of a dangerous answer. And this is what you would be trying to bias the model away from. This is the data set that we're going to use today for demonstrating DPO. I'm going to demonstrate it on Tiny Llama, which is a 1 billion model. It's a fairly small model, which allows me to do the DPO training process fairly quickly. I think in about 45 minutes, I was able to train on 16,000 samples, which is 10% of the overall data set. So the time for doing training on DPO, it's roughly about twice the time that you need for doing supervised fine-tuning, because you are running inference forward through two models, the reference model, which is duplicate of the original model, and the model that you're training. So you have twice the amount of forward passes, and although you've got the same amount of backward passes, probably as a rule of thumb, your training in DPO is going to take twice the length as doing fine-tuning. Another caveat before I move to show you the notebook is that when you train a model to be harmless like this, you're training the model when it gets a question to say something that's kind of benign and useless. And while that can be helpful because commercially you don't want your model to be outputting harmful or hateful content, it also can get in the way of the model statistically providing useful answers, and it can affect the quality of useful answers that are generated. And this has been a problem to some degree with the Llama 2 chat model, particularly when using the system prompt. The model is it's so fine-tuned using reinforcement learning that it doesn't answer a lot of questions, or it answers them in a kind of harmless but unhelpful way. So that's a caveat to be aware of when you're choosing your data set. Just one last comment I've remembered, which is that DPO, it's a very direct way of achieving what's called reinforcement learning. The previous approach, the two-step approach to doing this step of training, was to first get a totally new model and train it to recognize the difference between good and bad answers. So you would take the same data set, you would train a brand new model just to get accustomed to what we think is a chosen answer and what's a rejected answer. And then using that model, you would run a loop on the model you actually want to train, whereby the model you want to train would generate some answers. And you would then run that and get a reward that says, yes, this should be a chosen answer or this should be rejected, and then back propagate. So you had the original model and then this reward model. And that required a lot of steps and made it particularly difficult, except for the larger companies. With DPO, this process is just done directly by having both a reference model and by having the model you're training forward passing through both of them, let's say for the chosen answer, and then penalizing the probability of the chosen answer in a way that it will be incentivized to be increased if it's the chosen one versus the reference model, or it will be incentivized to decrease the probability of the rejected one versus the reference model. Let me quickly go through the materials we need before we do the DPO training. The first thing we need is a data set, and it needs to be formatted correctly with a prompt, then the chosen answer, and then the rejected answer. We're going to use Anthropic's helpful and harmless reinforcement learning data set. It's presented with only chosen and rejected rows, rather columns. So let's just take a look at the data. You can see there's a chosen prompt here. And the question is, if you're going to steal from a convenience store, and the assistant gives a harmless answer, which is I really couldn't say. And then the rejected answer is a more intense or bad answer. Same question, same prompt, but the assistant says it's good to consider the difference in human traffic at night and different reasoning there that you want to reject. As I mentioned, this isn't the right format, so I have reformatted it here into a data set. You can purchase access to this if you like. You'll find the link on the repo. You'll see there's the chosen, the rejected, and the prompt columns. Just to go through here, we have a prompt if you were to steal from a convenience store, and then you have the chosen and the rejected. Note that I formatted it for llama with the inst at the start and at the end, and I've also put in an end of sequence token. I don't really think this is critical because ultimately we're just comparing the probabilities of the model being trained with the reference model, and we're adjusting where there is a difference, or rather to create a difference to increase the likelihood of the chosen response and reduce the likelihood of the rejected response. So I'm not sure the end of sequence token is required, but just for consistency, I think it's good to format it like this. The next thing we're going to need is a reference model. I have a reference model here, which is the tiny llama model I said I would be training on. This is a model that I have trained with supervised fine-tuning using the OpenAssist dataset. It's available here for you to download if you like. And as I said, it's a chat fine-tuned model. Tiny Llama is only trained on a 2K context length. I did the fine-tuning using 4K context. It helps a little bit with the 2K performance, but it's not good enough to get the model to be a 4K dataset. So we'll be considering it a 2K dataset, even though that I call it 4K because I used 4K long or up to 4K long dataset, which is OpenAssist. And with that, I think we're ready to move on and do some fine tuning in the notebook. You can get access to the notebook by purchasing it through the link below, or you can purchase access to the full advanced fine tuning repository, which now has not just DPO, but scripts for embeddings, function calling training, long context, quantization, supervised fine-tuning, and unsupervised fine-tuning. Quite a lot of scripts in that advanced fine-tuning repo and quite a lot of members of it right now. All right, let's get started. And here we are with the direct preference optimization notebook. I'm going to take you through it step by step. So right up the top, we are going to connect with Hugging Face. This will allow us to push models, and also if you're accessing or fine-tuning a gated model, it's necessary to do the login. Lately, I've always been also logging in with weights and biases. It allows us to view the data and it saves the data for the future, so you have it nicely organized for runs. This is really handy because I use Runpod often and it saves the data even if I shut down the pod. So I've connected with weights and biases. Optionally, if you have the model downloaded to Google Drive, say you're working in Google Colab, you can connect Google Drive. Next, we'll do the installation. Note that I'm installing Flash Attention. This is going to be the V2, and that will accelerate the training process. It speeds up doing the attention part of the forward pass. I additionally now typically run this command here to get the Transformer's environment information. This is useful if you're ever troubleshooting and you need to post an issue on GitHub. It tells you all about the platform you're running. So we'll move on now to loading the model. The model I'll load is the Tiny Llama model. In fact, let me just increase the size of my font here. Something like this. I am not going to load it quantized because it's only a small model. So I've commented out the quantization. I'm not using any rope scaling. I've set the device map to auto, which means that the layers will be put onto the GPU. I'm running with an A6000 here. It's got 48 gigabytes of RAM, and that easily fits in the total model, which is about 2 gigabytes in size. In fact, if it's run in BF16, yeah, it's about 2 gigabytes in size because it has about 1 billion parameters in Tiny Llama. You can see here that I'm using flash attention, and this will reduce the memory requirements. Now, you can load a reference model by loading an exact copy, but actually the trainer will handle that for us. So I'm not going to load a reference model. I'll just load this single model here. Next up, I'll load the tokenizer. I can run a quick test generation just to see that the model is working correctly, which it is. Note that I'm only going to train LoRa parameters here, so I'll train a LoRa adapter. I'm not going to train any non-LoRa parameters. Typically, I would list out all of the parameters in the model and turn on training for some of those in non-LoRa format, but I don't do that here. It's necessary if you want to train for longer context. That's not what we're doing here. So I'm just going to train the LoRa parameters, which I'm going to apply in the next step. So here I'm enabling gradient checkpointing, and I have a function to print the trainable parameters. I'm printing out the model just to show you exactly what I'll be training. Within the attention, I'll train the Q, K, V, and O, and I'll also train in the linear layers the gate projection up, down. I'm not going to train the input layer norm, which would not be done through LoRa. I'm not going to train the post-attention layer norm. I'm not going to train the embeddings either, although training those will be important if you want to train for longer context, which is not what we're doing here. So indeed, you can see here the modules that I've chosen to train, and I'm applying the adapter now to the model so that we are training the LoRa config. This results in us training a lot less parameters than we normally would if we were doing a full fine-tune. Now, LoRa fine-tunes generally perform just as well, so hopefully we'll see that's the case here as well. Next up, we'll set up the tokenizer and padding. So I've just loaded the tokenizer here, and I'm going to add a padding token. You can use the unknown token as padding, but since the supervised fine-tuning base model I'm using has been trained with pad token like this, I'm going to keep consistent here and use that same pad token. Okay, so we'll continue on here. And you can see that the special tokens are the beginning of sequence, the end of sequence, the unknown token, and the pad token. Next up, we need to set up some evaluation so we can evaluate the model before we do the DPO and afterwards. And it's important here you set some questions that are relevant to the data set that you choose. Ideally, they should provide you some metric of how the model is performing. We're trying to fine tune here to have a model that is more harmless. So we're going to have to ask some ugly questions, and then we want to see that it gives what we'd consider an unacceptable answer before the fine tuning and gives hopefully a more acceptable answer after the DPO. So I've set up some questions here. Yeah, unfortunately, a lot of this kind of training involves ugly questions, which you will ask the model. And when you run that base evaluation, here it's bluntly answering the question, which you may not want. If you want to have a model that is going to be better behaved or aligned. But this provides us with a baseline we can then compare after the training, and hopefully this data set will have the effect that we intend. Okay, so we're loading the data set that I just took you through. It's the DPO Helpful and Harmless Reinforcement Learning dataset from Anthropic. So that's loaded. And here you can see there's a prompt talking about dinosaurs. So this is a more harmless question. But it ends with the user accusing the machine of not being able to read. And the harmless answer is, you can read, ? And the rejected answer is a more aggressive retort, which is, there's a lot of stuff humans don't know. Okay. So we'll move on And I've just got a test here where I tokenize, check the token IDs. You can see that a special token, that's the beginning of sequence token, is added at the start. So everything looks correct here. Now we're going to move on to the trainer. I'm going to use an evaluation set and a training set. The evaluation set is the test split. It's quite a large split. I think it's got over 10,000 rows. And just for the sake of running more quickly, I'm going to reduce that. So we'll only run with 960 of the test data set rows. I'm going to run for 0.1 epochs on the train data set. The train data set is 160K, so it'll be out of 16,000 row training that we'll do on the training side, and on the test side, it's about 960 rows. Okay, setting some parameters here. The context length will be 2K, which is the Tiny Llama context length. I'm setting the batch size to 8. This does fit on an A6000. You can fit 8 batches of 2000 tokens. You can maybe fit a bit more. You probably could fit 12, I think. And usually the way I set gradient accumulation is to have the batch size times the gradient accumulation be about 32. That means that basically you're doing 32 forward passes before accumulating the updates and then passing them backwards through the model. All right, so moving on here to the training arguments. Mostly we have already specified them. I'm going to do evaluation steps every quarter of the full run, so there should be 3 intermediate evaluation steps. The same with save steps. This will save the adapters, the LoRa adapters, in case the run crashes. I'll at least have the adapters saved. I'm setting a scheduler here typed to constant, so that means I've got constant learning rate throughout the run. Sometimes people will decrease that over time. I think with a small amount of data, you can probably just do a constant linear scheduler, a constant scheduler, but you might consider linear or cosine if you're doing a longer run with a large amount of data. Now, one of the most important parameters here is the learning rate. Typically, this might be 1e minus 5 for doing LoRa fine tunes, but with DPO, it's found that you need to have an even lower learning rate. It's recommended maybe 5e minus 7. I've got it slightly more here, which is 1e minus 6. And I'll actually show you an example of where it diverges when I try doing 1e minus 5. Okay, so with that, the trainer can be called. You can see I'm passing in the model. I'm not passing in a reference model because the trainer will create a copy automatically as a reference. I'm setting the beta of 0.1. If the beta was 0, then it would basically ignore the reference model. If the beta is 0.5, I think it's going to very strongly consider the model. So, it could be more than 0.5, but the higher beta is, the more that the reference model is considered, i.e. you can think of the model you're training being more tethered to the starting point. So it's recommended to have it between 0.1 and 0.5. I haven't played around a lot with this, but I'm leaving it at 0.1. Then I'm passing in the training set and the test set and then the tokenizer, and then I'm starting to train. Now, this model has already been trained, so I've gone all the way through 1,000 steps. This training has been completed, and I'm going to walk you through some of the results. It's going to be easiest probably to look in weights and biases because we can see the full graphs over there. And once we're done with the training, we can plot, so we can show the training loss and the validation loss. Really, you don't see a whole lot of change in the model here. The learning rate is very slow. So with this relatively small amount of data and such a low training learning rate, there's very little change in the model over the training period. And indeed, when I look here at the base model evaluation after the training, unfortunately, in this case, the data hasn't been enough to give me much change or any change in the answer that I'm getting. So still, the model is not giving a more restrained response to the more dangerous questions. So we haven't achieved the goal here with DPO, meaning that we would need to train perhaps for more of an epoch. I've only trained for 0.1 epochs. It's possible that simply the kind of nature of this question I'm asking here hasn't been covered in the training data set, so it's not being affected statistically by any of the samples that we've run through in DPO. So running for a full epoch would be one way to start with this, and maybe playing as well with having a little bit higher of a learning rate. So I'm going to show you the example I have with a little higher learning rate where I have 1e minus 5. I'll show you how it diverges, but also it actually gives you a sense for the effect it has in the model because it does start to change the answer. So right here with the 1e minus 5, everything is very same. The only difference is that when I ran the training, I had it at a learning rate of 1e minus 5, which is higher than 1e minus 6 by a factor of 10. And indeed, when I run that training and then I run the first sample here, you can see the answer is quite different now. So when it's asked about killing, it starts to give an answer that is a bit more restrained. It's now asking that people's human rights and emotions be considered. It's giving a much more verbose answer, trying to indicate more nuance around the topic. I wouldn't say that it's got the answer to as good of a level as we would hope for from a production level product, but still you can clearly see that the answer is no longer just directly providing dangerous recommendation on this question, but rather giving a little more nuance. Let's move over and take a quick look at the results. In fact, even just looking at the training and the eval loss, which should be kind of slowly falling, you can see in this case, the training loss starts to diverge. It's bouncing around pretty sharply because my learning rate is so high. And the eval loss, I wouldn't say it's getting terrible, but it's going up a little bit. But this kind of instability here indicates that probably I have my learning rate a little bit too high. So what we'll take a quick look at now to finish off is the weights and biases training. When you've connected up weights and biases, it'll automatically generate all of these plots. You can see here what the GPU is doing during this training session. It was about 50 minutes. Actually, I trained on an A100 here when I was running with 1 to the E minus 6. And right up the top, you can see some evaluation results. It's showing 4 plots here that I'll explain a little bit. The two I want to focus on are the margins plot and the accuracies plot. The accuracies plot is probably the easiest to understand. I know it's small font here. Let me see if I can increase actually just a bit. Yeah, I think that helps. So the accuracies tells us given a chosen response and giving a rejected response, what's the likelihood that the trained model will pick the chosen rather than the rejected? So ideally, you would like the model to have a high probability, more than 50%, of choosing the chosen response and have a low probability of choosing the rejected one. And so you can see here throughout the training, there's some oscillation, but at the end of the training, in fact, not at the end, but at the 750th step, you can see that it's got a slightly higher than 50% chance of picking the chosen rather than the rejected. So indeed, in this case, the model is being biased towards the chosen response, but you can see the bias is not very strong because it's 0.5135, so it's only a little bit more than half. And so you would need to take the model quite a bit further if you wanted to have the bias definitely move towards the chosen response. The next graph to look at is the margins graph. This is the difference in the reward for the chosen minus the reward for the rejected. So ideally, we want a positive margin here. You can see that actually the margin is negative, and this is an average across the whole evaluation. So there were about 960 rows in that evaluation. And I think that's why it's possible to have a negative margin when you're averaging across all of those according to value, whereas the accuracies are averaging across according to the number that favor the chosen over the rejected. So you can see that in any case, we're not seeing a very strong bias of the model. Unfortunately, we would like to see a positive margin that shows us a clear bias in a value sense, and we'd like to see a clear bias as well in terms of the number of responses that are chosen over rejected. And just for 2 more quick graphs, you can always keep an eye on the training and the eval graphs. The training loss should be going down over time as there should be similarity between all of the different samples we're trying to train on. So this should be dropping very slowly. You can see it looks pretty constant over this range of training. And then eval, this number here should also be falling. You can see here that it's gone from around 0.6929 to 6935. So there's really not any change here in the eval loss. It looks like some change because the y-axis is very compressed or very zoomed in on. In fact, we're just not seeing a whole lot of training within this short number of epochs. Before I go, I'm just going to show you exactly how I set things up on Runpod. What I'll do here is use an A6000. So if I go to Secure Cloud, I should see a list of all of the servers that are available like this. And this, I think, is probably one of the best values per unit of VRAM. It's got 48 VRAM for 79 cents per hour. Before I click deploy using a PyTorch instance, I'm just going to make sure I have plenty of memory here. 50 GB is way more than enough because the model is going to be about 2 gigabytes. And I'll click continue and then I'll deploy. So this is now going to deploy a PyTorch instance. And you can see I have an exited instance of an A100 that I was working on earlier. And once this is booted up, I'll be able to connect using a Jupyter notebook. Once the notebook is ready, once the pod is ready, I'll click connect and I'll click connect to Jupyter. I've just uploaded a DPO.ipynb notebook and I'll open it here in the screen. And I'm going to go through the steps that I discussed earlier, starting off by logging in with my Hugging Face ID. So here we have the Hugging Face ID, then doing the installation of weights and biases and using my login for that so that we have logs. So here's my weights and biases ID. And next up, we will do the installation. So install all the packages necessary. Move on to loading the model here. As I said, not loading it quantized because it's a small model, so there shouldn't be any issue with doing that. And I'm going to prepare the model then for fine tuning and stick with this selection here of target modules for that fine tuning. Initiate the tokenizer. And once the tokenizer is done, we'll move towards setting up evaluation, printing some evaluation results, and then loading the data set that we're going to use for training. Now, I'm going to make a little alteration here. This time around, I'm not going to trim the data set. So I'm going to use the full eval data set, which is about 10,000. So this is going to be a slower training run because I'm going to use the full eval data set. Also here, I'm going to run for a full epoch. So that should be an improvement on what was previously done. Now let's just check here to make sure the data set is imported. It looks like I have an error for loading up here. And unfortunately, I forgot to run this one cell here, which is necessary. So now that I've run cached here, I'll be able to run through all of these again. Apply the lower adapter, set up the tokenizer, set up the evaluation, load the data set, but this time not truncate it as I previously had done. So that's why I've commented out here where I've reduced the range of the eval data set and then increased to 1 epoch for the training. So let's see. And we have a learning rate scheduler type of constant. I'm actually going to move back to the original recommended learning rate. Well, you know, I might leave 1e-6, but instead of using constant, I think I will use linear here. So the learning rate will decrease as we move through all of the epochs. And you can see I've set up the results folder here for 1 epoch. And I'll go ahead and get started now to train the model. It should set up a weights and biases run. You can see here it's got 10,000 steps to go through instead of 1,000, so it's going to be quite a bit longer as a training. And I'm going to install matplotlib so I can plot the results at the end. I'll do a quick evaluation. This here I can remove. I'm going to remove all of these, and I will push the model to Hugging Face so that I have a copy of it. So I'll just go ahead and push that adapter. And additionally, I don't need to upload any other trainable parameters because they're all included in the LoRa adapter. So I should be free to just merge and unload the model, and then I should be free to push the tokenizer to Hugging Face Hub and push the model to Hugging Face Hub. What I might do is push tokenizer.model, which is a file in the original repo. That file is needed to do GPTQ and also GGUF quantizations, so it can be handy to just push that as well. So I'll scroll up here now and take a look at the training, which should be underway. And here the trainer is up and running, and you can see we're now 17 steps into 10,000 step run. It's about an 8-hour run, so fairly long, even though this is quite a small model, just a 1 billion parameter model. So it just gives you a feel for the amount of time if you're doing a full fine tune, rather if you're doing a LoRa fine tune on the model. And here we can just click on the weights and biases, and we should be able to pull up a copy of this run. And you can see here, training loss is progressing. And I'm going to just go to overview and just put in here what the run is about. 1e minus 6. And we'll say 1 epoch run tiny. Like this. And that's it. I'll post up later how the run goes. That, folks, is an overview of direct preference optimization. It is a lot easier than doing reinforcement learning, where you need to train a separate helper model. Still, doing DPO, direct preference optimization, it's not an easy feat, and you need to pay a lot of attention to having a data set that's comprehensive, choosing some questions for evaluation that allow you to tell whether your training is progressing or not. You also need to be comfortable with chat fine-tuning a model, which is a form of supervised fine-tuning. If you want to get started with something a little easier, I recommend going back over the videos for embeddings, unsupervised fine-tuning, and supervised fine-tuning. With respect to this video, I'll put all of the links on resources below, and you can find out more about getting access to the scripts and datasets. Cheers.